All right. So
Okay, so our speaker today is Jason Atnip, who's a postdoc at UNSW. So take it away.
all right. Thank you, Lachlan, and thank you everyone for joining us today, from wherever you are. So we're going to talk about random dynamical systems, random maps of the interval, and establishing a thermodynamic formalism. So what I'm going to talk about today is joint work with Gary Froyland, Cecilia Gonzalez-Tachman, and Sandro Vaienti. Okay, and like I just said, our goal is to establish a complete thermodynamic formalism for random piecewise expanding maps of the interval. And before I keep going, if you have any questions, I'll try and monitor the chat, but if you just want to pop in, feel free. Okay, but so our basic goals are we're going to look for conformal and invariant measures. Then we want to show these invariant measures are unique and in fact are random equilibrium states, and then show further that these measures satisfy an exponential decay of correlations. Okay. So our work is going to generalize the work of Liverani-Saussol-Vaienti in the deterministic setting, and we're going to mainly pull techniques from Buzzi and Myers, Skorolski, and Urbanski from the random setting. Okay. So maybe a little bit about what a random dynamical system is before we keep going. So in its most general sense, it's mainly composed of two big pieces. So we have a probability space in the base, and we'll call this the base dynamical system. So map sigma from a space omega to itself. And usually, as will be in our case, we'll have some extra assumptions on this space omega. We'll require it to be measure preserving, ergodic, and invertible. Okay. And then for the fibers, we have some space X and some family of maps T omega that take X into itself. And we'll iterate according to composing these based on the dynamical system in the base. Okay, so maybe why we should care about these sorts of things. Well, these random dynamical systems model real world complex systems better than deterministic dynamical systems. For example, we could have ocean or atmospheric flows whose models are based on parameters. So we could have this random dynamical system which changes based on the parameters, which may be changed seasonally. Okay, so here this random driving is coming from the seasonal changes. So more specifically, we're going to look at random piecewise monotone maps of the unit interval or any interval. But like I said, we'll have our dynamical system in the base. We'll have our map sigma be measure preserving, invertible, and ergodic. Okay, and then for each omega fiber in the base, we'll have a map T omega, which takes the interval onto itself. And we'll also assume that for each fiber, for each omega, there's a finite partition, z omega of the interval I, such that T omega of z is also an interval for each z, and T omega restricted to z is continuous and strictly monotone. Okay. Now, I should say for all of the results I'm going to talk about today, we can do the exact same thing for countable partitions. In that case, some of the assumptions that I'm going to tell you will be a little bit more complicated in the countable case, and we'll need a few extra assumptions. But for the purposes of this talk, let's just keep things simple, and we'll talk about finite partitions. Okay, so finitely branched maps. So our main tool is going to be the transfer operator. But to do that first, we need to talk about a class of functions for it to act on. And we'll be working with bounded variation functions. So just to remind you what that is, a function is a bounded variation if it is a bounded function and this number variation of f is finite. And here this supremum is taken over the collection of all finite partitions of the interval I. Okay. So the space BTI is a Banach space, and we'll consider it with the norm, which is sup norm plus the variation. And then we want to look at random functions or functions that change on the fibers. So that will look like BV omega, and this will be the space of all functions which are BV on every fiber, and the BV norm is measurable. Okay. So now, like I said, our main tool is going to be the transfer operator. So to define that, we'll first say that SNT of F is going to be our Birkhoff sum of F with respect to our fiber maps T. We could also replace the T with, say, a sigma, and then we'd be talking about the Birkhoff sum along the base dynamical system. The T is here just to tell us we're working with fibers. Okay. And the other piece we'll need is we're going to talk about general potentials. So we'll take a function phi in BV omega. And for each omega, we'll associate the weight function g omega, which is just x of phi. Okay. And then finally, we define our transfer operator to be the sum of g times f along over preimages. Okay. If phi omega was just minus log t omega prime for each omega, then here we'd just be talking about the normal, usual Perron-Frobenius operator. Okay. So our main assumptions, we're going to assume a random covering property. Okay, and so what this means is that we'll take any subinterval j, okay, and the assumption is that we can find some integer m depending on j and the fiber omega. So this m omega j such that for any n larger than this, if we push forward our transfer operator in steps for the function 1, the indicator function 1 of the interval j, it is going to be positive and bounded away from 0 by some constant. Okay. For our finite branched maps, this is equivalent to the assumption that t omega n of j covers the whole interval I. Okay, so this is just saying that for each of these maps, for any small interval, we can eventually cover the whole interval. And we will also need the following measurability assumptions. That is that our map T is measurable, that our transfer operator preserves random bounded variation functions, and that the sup and the inf of L omega 1 are both log integrable. Now, we have two other additional assumptions, but they're a little technical, so I don't want to talk about them today. But basically, M5 and M6 just amount to saying something about the log integrability of the covering times of particular small intervals. We won't worry too much about those. Our last main assumption is we'll assume that our potential is contracting if we have the 1 over n log sup g omega n is eventually less than 1 over n log inf L omega n of 1. Okay. This is equivalent in this finite branch case via the subadditive ergodic theorem to finding some capital N1 and capital N2 such that these integral inequality applies. So this contracting potential assumption and the random covering or the covering assumption are both random analogs of what's in LSV in the deterministic setting. And this CP assumption is very close. In the deterministic setting, it essentially boils down to saying something like sup of phi is less than the pressure. Okay, less than the topological pressure. But we'll move on from there. So we'll call this system, this tuple, consisting of omega, sigma m, our interval I, our family T, and our potential phi. We'll call that a random weighted covering system if it satisfies these assumptions we've just discussed. Okay. And like I said, if we were talking about countable branch maps, we would also have to assume something about the summability of the potential, and then our contracting potential assumption becomes slightly different to kind of discard pathological cases, but this is basically it. Okay. Now, we said our first goal, our goals were to find conformal and invariant measures. So let's start by finding these conformal measures. We'll do that in the usual way, or one of the usual ways, by applying the Schauder-Tikhonov fixed point theorem. And we'll do that, we'll apply this theorem fiber-wise to these maps psi omega. So we'll end up with a fixed point for this map psi, which is a functional living in the dual of BV. The problem with that is that a functional in the dual of BV is not necessarily a measure. So to deal with this, we extend our functional so that it acts on continuous functions. From there, we can apply the Ries theorem to obtain an actual measure. And lastly, we go back and show that this measure nu that we found is actually equivalent, or not equivalent, but equal to our functional, our conformal fixed point functional that we found in BV. Okay. So we end up with this family of non-atomic Borel probability measures, which are positive on non-degenerate subintervals J. Okay, and they satisfy this conformal measure property. Now, we would like to say that these things are random measures. Okay, and eventually we will be able to say that, but right now we can't. So first, what is a random measure? A random measure is a family of measures mu omega on I, which satisfy this measurability property that for each Borel set, for each Borel subset of the interval I, the map omega maps to mu omega b is measurable. And the second property is that almost every omega, our measure mu omega b is a Borel probability measure. Now, the nice thing about random measures is that there's a sort of equivalence here with probability measures on the product, and that is that here we've written kind of one side of this equivalence is that given a family or a random probability measure, which is this family of measures, given a random measure, we can define a measure on the product omega cross I just by integrating first over the fibers and then with respect to n. Okay, so a random measure is very nice, and we can integrate across the fibers. The problem with our conformal family that we found so far is that while we do know that nu omega is a Borel probability measure for each omega, we don't know anything about the measurability of the map omega goes to nu omega of A for any Borel subset A. Okay, so we will eventually solve this problem by giving a limit characterization of our measures nu, and then showing that they're a limit of measurable functions, and thus we end up with our random measure. But we won't be able to get that limit characterization until we have some amount of cone contraction. Okay, so for now we're going to move on because we're also going to get our invariant density via this same cone contraction. So to start looking for our invariant density, first, what I mean by that is that we want some function q omega, which is a density for nu omega. And by invariant, I mean that it satisfies this fiber-wise invariance property with respect to the normalized operator, L tilde. Okay, and the important thing here is that L tilde is going to send densities to densities. Now, we'll get this density via Birkhoff cone techniques, but in order to do that, we need some control on the variation. So we start off by first proving this Lasota-Yorke inequality for our normalized operator. And we find, for any m, we find these measurable constants, q omega n and k omega n, such that we get this. Okay, well, that's nice, but I should tell you more about q and k. So q, I can give you a formula for it. It's just going to be log 9 times sup g omega n over nth L omega n of 1. And the nice thing is that this number is going to decay exponentially to 0, which is nice. The problem is that this exponential rate will be in terms of omega, and we would like to remove this omega dependence. And then for k, well, we don't know anything about k in terms of n. We can show that both of these q omega and k omega n's, if you fix n, both of these numbers are log integrable, but we don't know how k omega n grows with it. It could be super exponential. And before I move on, let me just point out this log 9 that appears in the q omega n. This is, the 9 is coming from the M5 and M6 assumptions. So it's not just magic. But so to deal with these two problems about q and k, we prove this second Lasota-Yorke inequality based on Boozy's work, where we'll deal with both of these. We'll be able to find some uniform and omega exponential decay for the first term attached to the variation term, and then we get control over the k omega n constant by finding some measurable constant that covers both. Okay. And now, so this is the Lasota-Yorke inequality that we want to work with moving forward. And we'll use that inequality specifically for our cone techniques. So first, maybe let's talk about what convex cones are and what Birkhoff did. So if you're not familiar with a convex cone, it is just the infinite dimensional version of just a regular Euclidean cone, and it satisfies these properties, these 1 through 4. And now what Birkhoff said was that if you have two vector spaces, each containing a cone, and if you have some positive linear operator which sends one cone into the other cone, then if you look at the Hilbert pseudometrics induced on each of these cones, we end up with a contraction. Okay, so that our positive linear operator L is a contraction from, say, cone 1 into cone 2. And we have an explicit formula that our contraction factor is the hyperbolic tangent of the diameter of the original cone divided by 4. So this is going to be very handy if we know that we have a finite diameter image, because we know that we're contracting by a very specific amount each time. And thus, if we keep pushing forward, we're contracting to something that has diameter 0. So we're going to some sort of fixed point. This is less helpful if we have an infinite dimensional image, because then we're maybe contracting, but we still have infinite dimension, or infinite diameter, rather. Okay. So these are abstract, very general cones. Let's talk about our random cones that we'll use. So we'll first start off with defining this C plus cone for each omega fiber, and this is just going to be all non-negative BV functions. And then for each A parameter positive, we can define the CA cone, which are just all the functions in C plus whose variation is less than A times their new integral. Okay. Now, a result from LSB gives us a nice formula for the Hilbert pseudometrics induced on these cones. In particular, that the theta plus distance is always less than or equal to the theta A distance. Okay. Now, with these cones, the idea is that we want to use Birkhoff's theorem, and we want to push forward by some amount so that one of our cone at our omega fiber is contained in the cone at the future fiber. Okay, well, this isn't going to work for every omega, but what we can do is for any epsilon sufficiently small, we can find some set of good fibers. We'll call this omega G, and this set of good fibers has almost full measure, so measure greater than 1 minus epsilon, and we'll let omega B be all the bad fibers that are left over. But the important detail about these good fibers is that we can find some number R star, some positive integer R star, and some specific cone parameter A, such that if you have any good fiber, if we push the A cone forward by R star steps using our normalized operator, we'll contract by a factor of 1/2. So we'll land in the A over 2 cone. And even more importantly, that the diameter of the image of our push forward is going to be less than some finite fixed number delta. Okay, so if we get this contraction with finite diameter, and now if we started on a bad fiber, well, we're not going to get contraction in time R star, but what we can do is we can find some number L, depending on omega, which is bigger than 2 and finite for almost every bad fiber, such that if we push forward by L times R star, we'll get contraction by a factor of 1/2, so we'll land in the A over 2 cone again. But this time, we're unable to say anything about the size of the diameter of the image. So, meaning that if we started off with an infinite diameter cone and we pushed forward by L times R star, we would know we'd be in the A over 2 cone in the future, but we wouldn't know anything about the size of the image. So it could very well still be infinite diameter as well. Okay. Now, moving forward, what will work for us is that we'll be able to use density arguments via Birkhoff's ergodic theorem to tell us that, well, we're not going to hit a bad fiber very often. We'll mostly be hitting good fibers, since the good fibers take up a set of measure greater than 1 minus epsilon. So the idea is that if we pick an omega fiber and we push forward, well, eventually, pretty soon, we'll hit a good fiber. We'll push forward by r star, and then we'll have finite diameter image, so that whenever we push forward, then we're either contracting even further in the good case, or the important property about the push forward on bad fibers is that our operator is non-expansive. So it's a weak contraction, meaning we're not going to make our diameter grow. It always at least shrink or stay the same. Okay. So what do we get then? We end up being able to say that we can find some number for each omega. We can find some number in 2 omega, such that if we push forward more than that n2, we end up with a Cauchy sequence. Okay, so that this L omega n of 1 forms a Cauchy sequence in our C plus cone, which is closed, and thus we converge to some density Q omega. Okay, and in fact, we show more than just that the theta plus distance is exponentially decaying. We actually are able to show that the sup norm distance is exponentially decaying using this go-between. Okay, and this is another property of these theta plus distances. Now, so also, I guess I should point out, I've written this cone contraction lemma in terms of where we're just pushing forward the 1 function. We can actually do this more generally, and we can push forward any VV function, but there's more assumptions that go along with that. And with the 1 function, it can be stated nice and cleanly. So what we have below about the sup norm of L minus n of F converging to Q omega is still true. Okay. Now, so I think we have enough time, so I'll talk about how we go about proving this a little bit. But something to notice here is that, let's try and be fancy. Here we're pushing forward from the minus n fiber. Okay, so the reason why we're doing that is that we want to find a density Q omega on the omega fiber. So the way to do that is to go backwards in steps and push forward in steps, so that we're always landing on the omega fiber, and then we'll look at what this sequence does as n goes to infinity. And like we just said, well, I guess this should really be a L sigma minus n of omega n tilde 1. That this sequence is Cauchy, and that this sequence is what's converging to our density Q omega. Okay. So briefly, the idea here is that if we look down here at the diagram, like I said, we want to end up on the omega fiber. So we're going to go backwards in steps to the sigma minus n fiber. And to show it's Cauchy, we'll also have our second function go back by L steps. And then the way this works, by those density arguments about good and bad fibers, and good fibers happening much more often than bad fibers, we can push forward by some amount, sigma I, Okay, so in the worst case scenario, if we go backwards, maybe we're starting at a bad fiber. Maybe sigma minus n omega is a bad fiber. And the idea then is that we'll push forward until we find a good fiber. And we know that that is going to be small, or that won't continue on forever. And that we have to find some good fiber because, like I said, our bad fibers have a relatively small proportion within a large orbit of length n. Okay, so in fact, this distance here from the minus n fiber up to here, we'll let this be our first good fiber. That's going to be a relatively small proportion of our interval, of our orbit length that we're pushing forward. So along this first bit, we at most get weak contraction. And then now along this last bit, this sigma c times r star, this is where we're going to get contraction and getting our finite diameter. Okay. So that's kind of the picture to have in mind about what's happening when we're pushing forward these cones. But we end up with this Cauchy sequence that converges to this invariant density. Now, with this invariant density, we can define our invariant measure. So for each omega, we let mu omega be q omega times nu omega. And then from this cone contraction, we get that the families nu omega and mu omega are unique. Well, the mu is unique modulo nu. But nu is unique, and that mu is T invariant in the sense that, in this fiberwise sense here. Okay. Now, to show these are random measures, like I said before, we use our cone contraction, and we were able to find this limit characterization for nu omega for each omega. And as our transfer operator is assumed to preserve these random BV functions, we have that this limit characterization is in terms of measurable functions. So our measure nu is in fact measurable, or that the map omega maps to nu omega is measurable. So we end up with nu omega and mu omega being random measures, like we wanted. Okay, so now the goal is to talk about properties of this random measure mu. We end up with quasi-compactness for each of these measures, meaning that we get this exponentially fast convergence to our density. And we do that, we find for each function f and bv omega 1, okay, so these are our functions in bv omega, where the bv norm is integrable with respect to m. But for each of these functions, we can find constants which, measurable constants which depend on f, such that we get this exponential decay. Okay, and here, for the second one, we have this in terms of the L hat operator, where this is our fully normalized operator. The important thing about this L hat operator is it sends the one function to the one function, just like the Brown-Frobenius operator would. Okay. So now, using this quasi-compactness, we are able to get that the invariant measure mu satisfies an exponential decay of correlations for these BV1 functions. Okay, and maybe one thing to point out, that if you look at this at first glance, you might not see it, but this term, this L1 norm of F, depends on N. So if you thought about this long enough, you might be worried that this term might grow within, or it might change as the fiber changes in such a way that the right-hand side doesn't actually decay exponentially. However, as a side effect of the fact that F is in L1, we get what's called temperedness, meaning that we can, rather 1 over n times this number goes to 0 as n goes to infinity. Okay, so we actually do get exponential decay in the right-hand side. And our last bit is we want to talk about random equilibrium states. Okay, so given our potential phi, first we need to define our expected topological pressure, and that is going to be EP of phi is going to be the integral of log lambda omega. And then for each t-invariant random probability measure eta, we can define the conditional information of the partition z omega given the pullback of the Borel sigma algebra. So we can define this conditional information with respect to eta omega. And here where this g eta omega is defined in terms of the conditional expectation with respect to eta omega. Okay. Now, using these, we can write, we come up with a variational principle for our measures in terms of phi. And then we get that the expected pressure is always going to be greater than or equal to this integral over omega of the integral of the information plus phi omega. Okay, so usually we would write an equilibrium state as a measure that that's equal to, or rather, we write it as a measure whose entropy plus the integral of our potential is equal to our pressure. This is going to be the case that we have here as well. We've just chosen to write it as the integral of our information because if we're working with countably branched maps, our entropy could also be infinite and our potential could also be infinite. So writing it this way kind of makes things more explicit when it's finite, but it does amount to being the exact same thing. And here we also show that our invariant measure mu is the unique random t-invariant measure which equal such that this quantity is equal to the expected pressure. Okay, so we get that it's the unique relative equilibrium state. Now, let's just summarize what all of our results are before we move on to examples. But what we came up with is if we have this random weighted covering system, we can find a unique random conformal probability measure nu that satisfies this conformal measure property. And here where lambda omega is log integrable, we're able to find a unique modulo nu invariant density, which is BV on every fiber and is invariant with respect to the normalized operator. Okay, from that we define this invariant measure mu, which is T invariant and ergodic, and is the unique equilibrium state unique relative equilibrium state for phi. And then we also get this quasi-compactness and exponential decay of correlations for these measures. Okay. So let's look at some examples. The prototypical example these sorts of systems are beta transformations. But let's look at maybe something a little bit more complicated. We can deal with maps with non-uniform expansion. So our first example, let's say we have two maps, T0 and T1. For our first map, let's just make it simple. We'll have a beta transformation where beta is greater than or equal to 2. So we have this kind of uniform and a uniform expansion there. And for our T1, we have the Moe-Manville map, which has a intermittent fixed point at 1. I'm sorry, at 0, which means that the derivative at 0 is equal to 1. So the problem would be if we had the map T1 composed with itself many, many times, it would take a very long time for any point close to 0 to map out away from 0. And what we can show is that if we have some geometric potential, meaning that phi omega is equal to minus t log t omega prime, for any t greater than or equal to 0, we can find some number delta sufficiently small such that if the probability of finding this bad T1 map is less than delta and still positive, then all of our results hold. Okay, so what's happening here is that since we see this map with these bad expanding properties, rarely enough, the expansion from the T0 map is able to overcome that, and we end up with this exponential decay of correlations. If we were in the deterministic case and we were only composing T1 with itself, we would end up with polynomial decay of correlations. Okay, and there's actually nothing special in this example with respect to the PM map. We could in fact replace the Moe-Manville map with one that has contracting branches. Okay, so where we have points whose derivative is even less than 1. So if we again look at a T0 map, which is just a beta transformation with beta greater than or equal to 2, and we replace our T1 map with this map that is contracting on this first branch, and then, well, we still one of our main assumptions was that each of these maps were onto, so we still need this to be onto. So here in the second branch, we have a full branch. So this map, maybe if I draw a small picture, looks something like this. Here we have some point where after that we have a full branch, and here we have this. Maybe this is not a great picture. Let's see if I can delete this branch. Here we have some contracting branch, which is not growing very much. Maybe there's the line y equals x. Then again, using the same arguments that we did in the previous example, we get all of our results holding. Okay, if we see this T1 map with small enough probability. Okay, maybe one last example. Maybe one kind of very large class of examples. So we can look at just random Lasota-Yorke maps, metric potential again. So this is phi omega is just minus t log t prime for any t greater than or equal to 0. And we'll further assume that each t omega is piecewise C2. And we want to assume a strong random covering assumption. So this is a strengthening of the random covering we talked about before. This is kind of where we have a, for each level n, we have a uniform and n, uniform over omega covering time. So our covering time is just a function of n and not omega. But this isn't totally unreasonable. We have random examples that satisfy this strong covering as well, so it's not too strong. And then we also will assume these next 5 assumptions. where we have some sort of distortion control over our derivatives. We want our derivatives to all be uniformly expanding between some little lambda and capital lambda, bigger than 1. All of our finite partitions are uniformly finite, so that means there's some number d such that the cardinality of z omega is less than d for every omega. We want, oh, here I should have changed this notation, but this log script I, this is just going to be the minimum of the number of pre-images for each branch. We want that to be log integrable and greater than or equal to, not greater than or equal to, but strictly greater than t log capital lambda over little lambda. And lastly, we want some control over the minimum size of the diameters for our partitions at the nth level. And if we have all of these things, then all of our theorems hold. And here we have all of these additional assumptions because we wanted to give some sort of guide on what you need to check for very general class of maps. But if we have more specific examples like we did before, or even just random beta transformations, most of these are already satisfied and we don't really need to assume too much more. Okay, but with that, I think I will stop and say thank you for listening, and let's see if you have any questions.